Good evening dear all. Today we shall do some numericals on Coulomb's law based on the formula formulated by the law. Okay. So first let us write down the formula which we have learned for forces between two charges placed at a distance r. Where k is a constant of proportionality and the medium is air, right? Now we have a numerical here. Let us read that numerical first. There are 2 point charges having equal charges separated by 1 meter distance experience a force of 8N. So here the information given to us is 2 charges are equal, separated by a distance of 1 meter and the force is given to us as 8N. So we will just write what is given to us on the board. Now let us substitute these values in the given formula of Coulomb's law. Therefore, F is equal to KQ square. Now, in the other part of the question, it is written that what will be the force experienced by them if they are held in water at the same distance. So, the information given in the next part is we have to find out F dash provided the charges are same. So, and the distance is also same between them. So, I write the formula of F dash as K dash Q square upon R square, which is already mentioned as the above K dash K Q square. So now I have F dash is equal to K dash Q square. Writing K dash is equal to 1 upon 4 pi epsilon naught epsilon R. We have K dash is equal to 1 upon 80K, where I have written 1 upon 4 pi epsilon naught as K and epsilon R is substituted as 80, which is given to us as 80. So we have K dash is equal to 1 upon 80K. Substituting the value of K dash in F dash, we have F dash is equal to 1 upon 80 K Q square. But KQ square is already given to us, found out by us as F. Therefore, F dash is equal to 1 upon 80 F. It means that the new force is 1 upon 80 times the old force when we change the medium from air to water. Now let us do a few numericals based on Coulomb's law, where we will try to connect theory to the numerical and numerical to the theory as a complete package of theory and numerical. So try to do that while studying itself. Okay, so let us talk about the numerical shown here. We have 2 insulated charged copper spheres A and B of identical size having charges QA and QB respectively. So let us draw 2 identical spheres A and B with the charges QA and QB respectively as given. Now let us read the next sentence. A third sphere C of the same size means identical but uncharged is brought in contact with the first and then in contact with the second and finally removed from both. Okay, so which means that I have third sphere which is uncharged, naming C, but it is identical to A and B. This sphere C as read here is first brought in contact with A then in contact with B, and then released as read in the sentence number 2. So when A comes in contact with C, according to the theory of conduction which we learned in the theory part, both the charges or both the spheres will get equal charges. So the charge on the sphere A will be QA by 2, and the charge on sphere C will also be QA by 2. Now this sphere C is removed from A and kept in contact with B. So this sphere C has QA upon 2. It was originally uncharged, and now we are keeping it in contact with B. So the new charge on B and C will be addition of both divided by 2. So the sphere B will have QB plus QA upon 2 divided by 2. Similarly, the sphere C will also have QA by 2 plus QB divided by 2. So the question here is, what is the new charge on A and B? The new charge on A is QA by 2. The new charge on B is QA upon 2 plus QB. As per conduction, it should be distributed equally, so I divide by 2. They can also ask, which is not asked here, what is the charge on C? The charge on C is also the same, because in the end the sphere C was detached both from A and B. It took half charge from here, it took another charge from here, divided by 2. Okay, now let us consider one application or a numerical of Coulomb's law. Now, according to Coulomb's law, force between two charges is inversely proportional to r square, or if we read it in the other way, force between two charges is directly proportional to 1 upon r square. So when we say the word directly, it is definitely going to be a straight line graph from the origin. Now in the question, it is written as plot a graph showing the variation of Coulomb force F versus 1 upon r square. So written force on the y-axis and 1 upon r square on the x-axis, where r is the distance between the two charges of each pair of charges. Now we have a pair of charge here which are both positive. It means we have to plot a graph in the first quadrant of the graph sheet or coordinate system. So using that property, let us draw the graph as a straight line graph, because it is just now explained that force is directly proportional to 1 upon r square. Here we have F and here we have 1 upon r square. So we have a straight line graph of 1 microcoulomb and 2 microcoulomb. Now we have another point which is given to us as 2 microcoulomb and negative 3 microcoulomb. It means that one of the charge is negative and the other charge is positive. So the force which we have on the graph is definitely going to be a negative. So we plot a graph in the fourth quadrant. Okay, so we can write it as 2 microcoulomb and negative 3 microcoulomb. So the first part of question is plot the graph. We have plotted the graph. If at all both the charges are positive, we draw it in the first quadrant. If both the charges are of different polarity, we draw it in the fourth quadrant. Similarly, the other two quadrants, we can draw the graph according to the polarity given for the charges. Okay, the next part of the question is interpret the graphs obtained. What is the interpretation? It is a straight line graph. That is the first interpretation. It is a straight line graph. That is the first interpretation. Second interpretation is that the value of Q1, Q2 for the first 2 points is 1 into 2 micro square, Coulomb square, right? And the value of Q1 dash and Q2 dash in the next pair is 2 into negative 3 micro square Coulomb square, which is equal to negative 6 micro square Coulomb square. Here we can see the magnitude of the product of the two charges is different. The product of the two charges magnitude for the first pair is 2 and for the next pair it is 6. So the slope for the first pair should be less compared to the slope for the next pair. That is the second interpretation. Here we can write slope less and here we can write slope more. And the third interpretation is, as you can see, this force is repulsive and this force is attractive in the fourth quadrant always. These are the interpretations you can give for the second part of the question. Okay. So we do another numerical based on Coulomb's law. Let us read the numerical. What is the force of repulsion if each sphere is charged double and the distance between them is halved? So we rewrite the formula of the law. F is equal to K, Q1, Q2 upon R square. Now what is given to us? It is given that the sphere is charged double. Each sphere is charged double. So let us write another charge Q dash is equal to 2Q1, which is double than the old one, and Q double dash, which is equal to 2Q2, which is double than the old one. It is also given to us that the distance is halved. So let us write R dash is equal to R upon 2. Okay, so let us substitute these values in the new force due to the new given charges and the new given distance, which is given as F dash is equal to K Q dash Q double dash upon R dash. Substituting these values, we have F dash is equal to K 2Q1 2Q2 upon R dash, which is R upon 2 square. Okay, so let us solve this now. We get K 2 to the 4 Q1 Q2 upon R square upon 4, which I have placed in the bracket, such that F dash is equal to K 4 Q1 Q2 upon R square multiplied by 4, which is a reciprocal of the denominator. Therefore, F dash is equal to 4 into 4, 16 K Q1 Q2 upon R square. Here K Q1 Q2 upon R square is F. Therefore, we have F dash is equal to 16 F. So this is a new force which is 16 times the old force, which was the original setup of the charges and the distance between them. Okay, so let us consider one numerical based on how force on a system of charges is in equilibrium. Whenever we say about equilibrium of a system for the charges, we automatically have to remember that the net force should be 0 on the system of charges. Only then the system of charges is said to be in equilibrium. Then there are two types of equilibriums. One is stable and the other one is unstable. For stable equilibrium, when we shift the charge, it returns back to its original position when we leave it. If the system is in unstable equilibrium, when we shift the charge this side or that side and we leave it, it remains moving in any other position. It will not come back to its original position. Then we say that the system of charges is in unstable equilibrium. So let us see whether it is stable or unstable or neutral equilibrium. Okay, so that is neutral is stable equilibrium. Okay, so now here they have given us 2 electrons. That's why I have written negative here and negative E here, which indicates that we are placing 2 electrons along a straight line, and a positive charge. It is written here as a positive charge Q. So I have written a positive charge Q here at any position, they said, and we have to understand at what position and for what value of Q will the system be in equilibrium. So let us first consider that Q is placed at the center of the line joining the 2 electrons. So this portion has a distance x from the origin O, center O, and the other portion is also x from the center O. Now for the forces on the charge Q to be equal to 0, we can write force due to electron on plus Q is F is equal to K EQQ charge 1 charge 2 upon x square. Similarly, we can write for the other portion also F, we can indicate this as FQ, this also as FQ from the other side is also equal to K EQQ upon x square according to the Coulomb's law. You can see the magnitudes are same, but what about the direction of these forces? These 2 forces are attractive because the polarity is opposite. This force is also attractive because the polarity of this combination and pair is not the same. So on the charge Q, the force due to this electron is this side and the force due to that electron is that side, the other side. So the total force or the net force on the charge Q becomes 0 because the magnitude is the same and the direction is opposite due to these 2 charges. Okay, so now let us calculate the force at A or B, that is on the electron placed at A or B. So we denote it as Fe minus, whether for A or whether for B. So now what is the force on the electron at A? It is due to the charge plus Q. It is also due to the charge minus E, that is the electron. So first we will talk about the F minus E due to Q plus Q. So what is the value of that? F is equal to K minus E Q product of the charges divided by the distance square. Okay. The next charge is also exerting a force which is between AO here, we'll denote it like that, which is due to AB, force on A due to B, force on A due to the charge on O. So that is K minus E, again minus E, negative E divided by 2x whole square. Now, I have mentioned here 2x because the distance between these 2 charges, that is the electron and that electron, is 2x. The distance between this electron and the plus Q charge is x, so I have mentioned x here. So the force to be 0 or the system to be in equilibrium, the addition of these 2 forces should be equal to 0. So let us add these 2 forces. Net force should be equal to 0. So this force I have added with, I'll multiply it, minus into minus plus, so I'll write here E square upon 4x square should be equal to 0. Now we have to find the value for Q such that the force is equal to 0. So anyway you can find out, the best way to find out is take it the other way around, minus K EQ divided by x square is equal to, I take it that side, that also becomes negative K E square divided by 4x square. So x square I cancel, K I cancel, 1 E and another E I cancel. So what am I left out with? This is negative, so it becomes plus on both the sides. I'm left out with Q is equal to 1E upon 4. So as per the question asked, at what position and for what value of Q will the system be in equilibrium? So for what position the system will be in equilibrium? The position of plus Q is at center O, then the total force is equal to 0. So plus Q should be kept at the center. Then the system will be in equilibrium. So the position is center. Okay. That is should be mentioned in the answer. Position center of the line joining minus E, that is the two electrons. The equilibrium will be attained. What value? For what value? What did we do? We started calculating from here. We calculated that the force for the electron due to plus Q, force on the electron due to the another electron having the charge minus Q. We said that already it is in equilibrium, or if it has to be in equilibrium, the net force should be equal to 0, and calculated the value of Q which is asked for equilibrium, which is equal to Q is equal to E by 4. Now there is another part of the question which is asking you whether the system is in stable, unstable, equilibrium. Okay, so let us shift this charge plus Q this side, or even we can shift it that side. If I shift it this side, will it go back to its original position? No, because this is negative, this is positive, it will attract, so it will not go back to its original position. That's why the equilibrium in this case is said to be unstable. Same thing will happen if I shift this charge plus Q that side. It will attract, so it will go away towards B, and it will not come to its original position O. So this equilibrium is unstable equilibrium. So what is the first part? Position of the plus Q should be at the center. What is the value of Q? E by 4. What is the equilibrium? Stable. This should be the last part of your answer in written, because the result answer carries marks of half in the board marking scheme. So remember, after finishing the numerical, write as the last part values of whatever is asked in this way. That carries marks. Remember that. Okay. Okay. So now let us move to another question based on Coulomb's law, which is just like the previous question, but here the polarity of charges is little bit different. Here we have two charges. All the three are positive, and we have to show that the system is in equilibrium. Let us read the question. A charge Q is placed at the center of line joining two equal charges Q and Q. Show that the system of the three charges will be in equilibrium if Q is equal to minus Q upon 4. So let us consider first of all that the system of charges is in equilibrium. What has to be done? So we have to first show that total FQ, force on small q, is equal to 0, and the force on capital Q at A and B is also equal to 0 separately. So let us consider the force on the charge Q at the center. They have already given us that it is placed at the center, Q is placed at the center. So let us consider this as X, this as X. So let us first find out F Q Q, which is equal to K Q Q upon X squared. Similarly, from the other side, let us find out F Q Q, that is equal to K Q Q upon X squared. As you can see, both the magnitudes are same. So for equilibrium, the addition of these two forces should be equal to 0. Substituting, we get FQQ is equal to negative FQQ from both the sides, showing that magnitudes are same and directions are opposite. Clear? So the total force on Q is equal to 0. Now let us show that F capital Q, either this side or that side, is equal to 0. For that, let us calculate the force at A. So F Q, capital Q, small q, force on this Q due to this Q is equal to K, QQ, distance between these Q and this Q is X square. Similarly, force on Q due to capital Q is equal to K QQ upon 2x whole square. Why? Because distance between these two charges is 2x and I square it, so it becomes 2x square. So now let me add these two forces such that we get the total force on this charge equal to 0. Therefore, this is simple way of doing maths. There are many other ways. Whichever is convenient, you can follow that according to your easiness or your quickness. So now what are we left out with? We are left out with the value of Q is equal to negative Q upon 4, which is the condition in the question given to us and should be proved by us such that the system is in equilibrium. We took the system in equilibrium and found out the value of Q is equal to minus Q by 4, which was asked to be proved in the question.